Okay, moving on to our next set of slides, we're going to be talking about the potholes that you can fall in when making maps. The first thing I want to talk about is building on the Monmouth book, How to Lie with Maps, is that all maps lie, and I put lie in little air quotes. But what we're talking about is abstracting reality, and when we do that, we have to generalize, which can introduce bias, and I'm going to talk about all this in a second. Okay, so how do maps lie? First of all, we're distorting them when we move from 3D curved surface down to a two-dimensional plane. We're abstracting reality. We have to. So we're simplifying and taking complicated features, simplifying them. So we're going to lose information, right? There's lots of ways that abstraction is going to result in loss of detail. We're going to do different processing or analyses to erode the precision. We can smooth, which is a misrepresentation of reality, but it's also necessary depending on scale. Blatant mistakes, whether it's humans doing digitizing or entering data incorrectly, accidentally moving something, which it could go back to how we're distorting. And then just making deliberate errors, things that we need to do to make a map work, moving things around, labels, things like that. And then it is a good choice of words to say a deliberate error, but if we're choosing what we're going to put on a map and what we're not, we are making deliberate choices. Is it an error? Well, it depends on how you define error. It's not 100% correct anymore. So it's artificial. So anyway, just a short list of how maps can lie. If you haven't read Mark Monmouth's book, it is fantastic. And I've got a PDF in the readings for the next couple of weeks. That's a summary kind of, I think, where he got his idea for the bigger book. And I hope you'll take a look at that. Okay, cartographic transformations, 3D to 2D. We've talked about this a ton in GIS. The Earth is obviously a curved surface. We have to go through a whole bunch of mathematical transformations to get it to a flat plane. First of all, we have to fit an ellipsoid, a 3D model, to the geoid, which gives us a proxy for sea level, in order to obtain a workable, mathematically modelable 3D surface that's going to mimic the Earth's surface. So we've taken a whole bunch of assumptions there already. Second, we're going to figure out some math to flatten this curved surface so that we can do our analyses on it. Even if it's just projecting it onto a flat computer screen, we're still losing information, whether it's the other side of the globe that we can't see at the same time we see the one we're looking at, or distortions that happen in projections. Once we get it onto a flat plane, or even if we are looking at it in 3D, we have to generalize. If you're looking at the entire globe, you can't see the tops of all the houses in a city. So we have generalizations that happen depending on the scale. Okay, so let's talk about some generalizations. There's basically I'm going to talk about 3 different types. They all result in a loss of information, but they're all necessary because we have to reduce complexity. We can't represent the whole Earth exactly as it is. That's insane. But all are going to introduce bias and can cause unwanted effects. So you have to be careful. So one way is simplifying, getting rid of things that we don't want to look at a certain scale because it just clouds the image. And that can include types of aggregation where you're classifying to help reduce complexity. So here you can see we've got individual points, but then we took this cluster and we're representing it as a shape instead. We might simplify by straightening out a river, and you see this with river data sets, whether a channel is derived from a LiDAR data set versus like a 1 to 24,000 USGS topo map. You're going to get very different levels of detail in the polyline. But what they're trying to draw attention to here is that you may have 2 locations mapped that are both on, this bank of the river. But when you artificially straighten this to generalize the river for a different scale, it may put the river in between your two study sites, for example, and now all of a sudden they're on opposite banks of this channel. So you just have to be careful about the choices that you're making and what kind of impacts it has. Symbolization, mimetic or abstract. So are we using symbols that we can intuitively connect to, or symbols that are somewhat objective? It's also called emotive symbology, where you're using like a cartoon or a character, versus objective symbology that may not introduce as much emotional kind of bias, but may be more cognitively challenging to decode. Okay, so we've talked about all maps lying for a lot of different reasons, mistakes, eroding precision, etc. Let's talk about choropleth maps. This is one of the most common ways of mapping data and not just locations. What we're talking about is aggregating or classifying and then giving each aerial unit a color based on the numeric values that fall into those classes. So if we choose to not classify, we may start with just a color ramp or a color scheme like this, and then we're going to have if we've got continuous values, we're just going to have an evenly distributed spread of values over the color ramp. And look at the difference between the two maps. The difference here, what we can't see, is the histogram. We've got 50 states, or 48 here, and we don't know how the values for each state are being distributed along this color ramp, except we have a pretty good idea that we've got an outlier that's very high and a whole bunch of the states that are down here in the 0 to 3. So when you classify, we can break this up a little bit differently. Here we've got 0 to 0.4, 0.6 to 1.2, 1.5 to 3.1. So here we've gotten all of these values that are falling under 4, or whatever this is, and we've put those in the bottom 3 classes, spreading things out a little bit more. And we still have our outlier, main, but we've gotten a different looking distribution on the map. But think about what a different story you're telling here, right? And if you aren't transparent and making your classes very obvious here, you are also imparting bias. Okay, data classification. The way that you break up your numeric distribution of values way affects the message that you're conveying. Okay, that's what I'm talking about when I say introducing bias. You have to be very transparent and very deliberate about how you choose your data classification. And I think one of the easiest things it is to do with ARC, because ARC, when you map up data, automatically classifies it for you. It throws the Jenks natural breaks classification scheme on your data. And if you don't think about that and deliberately change it, you're letting ARC control your life, and you shouldn't ever do that. It would be better, I think, and make more sense if ARC would just put your data in unclassified and let it be distributed along the color scheme, and let you choose a classification scheme. So anyway, we need to talk about a couple of things. Number one, the number of classes that you're going to use, which is interesting, but not nearly as interesting as the way that you're breaking up the classes. So here's we've talked about these before in GIS, natural breaks. This is the Jenks, that's the default in ARC. There's geometric classification schemes, equal interval classification schemes, and you can see you get a very different look. So let's break those down briefly. Here's a data set with a bunch of, I think this was meant to be rainfall or something like that. And you can see that we've pulled some basic summary statistics. We've got a min of 20, a max of 91. The average is 50.35. We've got a median around 50. And there's 80 different values. So how could you encode this on a map? What would you do? Where would you start? I'd argue you should start by knowing the distribution of your data. Make a histogram and look at it. This is how it breaks down. We have 12 different values that are coming in between 48 and 52. That makes perfect sense because that encapsulates both the average and the median. 80 different observations distributed like this. Okay, so how could you imagine grouping this data? How many different classes they say that the optimum number of classes is usually between 4 and 6, but it just depends. All right, so equal interval, defined interval. This is up to the user to say where they want their breaks to fall. So 20 to 40, 40 to 60, 60 to 80 makes a very clean legend, but doesn't relate very well to the distribution of the data. The Jenks natural breaks looks for, guess what? Natural breaks in the data. So it might break up the distribution like this. Same number of classes, just distributed a little bit differently. So these natural breaks, the groups are created based on similarities within each group. It can be done automatically, manually, or using mathematical algorithms, but the histogram definitely aids in doing that manually. Just so we talk through the rest, a quartile means that 25%, a quarter of all the observations are going to be put into each class. So some of the classes may have a much smaller span if there's more observations. And then if there are very few observations, the span may be much greater. And here's just an example of that. We've got equal interval up here where we've got the same, the spread in the breaks are the same, and then we've got quantile where the number of observations in each class is the same. So if you look carefully at the values here, you'll see that the classes are quite different, and the story it tells on the page is much different. So what if you were looking at a comparison between two different counties? Like here, if you look, well, even, geez, some of these here, if you look, we've got almost neighboring counties that are in the extremes from low to high. And here, they're next to each other in the classification scheme. That's kind of a big deal. So, and yeah, this is another example of that. You have to be very careful. Notice that I'm not giving you rules. I'm just telling you what to be aware of. Okay, this is another interesting way to classify is using standard deviation. It helps illustrate how far away a feature's value is from the mean. And this is just another option that you can choose when you're setting up your classification in ArcGIS. Beware, this is for normal distributions of data, so you should definitely look at the histogram which Arc gives you and only apply this when you've got a somewhat normal distribution for data. And the other thing is Arc will automatically give you a divergent color ramp, but you're going to want to make sure that you employ a color ramp that uses one color for positive, one value for neutral, and one color for negatives. Okay, I show you this example, which is poorly animated, to show that same idea that depending on, so here we've just got a completely made up data set with counties that are alphabetical and the percent of the population living on an active farm, completely made up. But depending on how you classify, the two counties in question here are in different classes just based on the classification scheme. So if you're trying to, convey information, you've got people looking, you would say, wow, these two countries are very different from, or counties are very different from each other. And that's not actually the case. So you have to be aware of these things. So classification methods should do two things. One, maximize the differences between the classes, but also minimize the differences within the class. So if you go back to, I'm going to flip through this and go back to here, when we look at this, the Jenks natural breaks has actually quite a bit of difference between the data sets. And it might make more sense to classify these values together, classify all the low values together, right? So that you have like values being clumped together. Okay. Yeah, all right. So geometric interval was a classification scheme that was created to basically hybrid between equal interval, natural breaks, and quantile. It's kind of a best of all worlds type of classification scheme. You definitely only want to use this for continuous data, slope, elevation, rainfall, etc. And it tries to create a balance between highlighting the changes in the middle values and the extreme values. So a good, like an example of when you might want to use this is if you've got 100 weather stations and only 15 out of the 100 actually had recorded precipitation, you've got a bunch with 0, that would be a good time to use geometric interval, because it's going to give you a more logical, it won't be, all those 0 values won't skew the data quite as hard, or sorry, skew the distribution of your colors in your map quite as much. Yeah. Okay, so that's kind of step 1 of talking through some of the common pitfalls, and next we're going to get into the modifiable unit area problem.